have here Professor Orlando Rojas. He is the Canada Excellence Research Chair as well as the Director of the Bio Institute at the UBC, the beautiful campus in Vancouver. He is an extremely distinguished scholar. I will not go through the bio for the sake of interest of time, but we are so happy that he is back after 5 years, I guess.
Yes, 5 years.
The weather is perfect, is more warmer than Vancouver. So perhaps you can think about moving to Waterloo. This is always like this. It's always warm here in Waterloo. So welcome, Orlando. We look forward to your talk as well.
Thank you, Professor Mitra. A pleasure. Yeah, thank you so much. I have enjoyed the last 2 days here visiting campus. You have a very energetic crowd, students, faculty. I'm also very happy to meet old friends and new friends. I'm also very happy that the room is full of students, researchers, and young generation. So I will be talking about bio-based colloids in terms of gelation and green interfaces. What I did here is to put some few slides with some highlights of our work, but it's a very small window to the bigger picture of activities that we have in our group in University of British Columbia. So I like to remind myself about historical, traditional aspects, and in that context, I also want to look and bring the simplicity of life back to the picture, even when it comes to nanotechnologies. And what you see on the left, you have had the chance to read a little bit about it. That's a former PhD student that made an aquarella, and in a way shows what we try to do at the interface between material science and the chemistry of interfaces involving water, including gelation and biological activity as well. So first, I want to go very simple and talk about wood. And I don't know if you have seen this news in a year ago or 2 years ago about the evidence for the earliest structural use of wood close to 500,000 years ago. This is absolutely amazing. Our civilization and before having using wood for construction and structural materials. And this was preserved in the mud, and today we have evidence for this type of materials. So from the materials point of view, wood is one of my favorite examples. And back to the simplicity of wood that we know every day. Then I also want to bring a little bit one thing that I did maybe 2 years ago. I visited my hometown in the Andes, in my home country of Venezuela. And then I found a person that has a toy museum that is absolutely fantastic. And I spent a full day learning about the science of toys. And one thing that I concluded after the visit is that the toys have been evolved since 4,000 before Christ, when we use sticks, rocks, and stone, and it has evolved into wood, celluloids, tin, plastic, and now back to wood. So wood is back, and that's why on the far right, I allude to the back to the future, because some of the most beautiful technologies are based on this old material, and I love that. That on itself is, to me, amazing for us to reflect. So the piece of wood that now you see is a dead tree that my son cut in his little house. He made this cut in the middle, and that revealed the beauty of wood in its internal structure. So you see the fibers, the colors, the connections, and I just fell in love with this image, right? So credits to my son, who also admires the power of wood. And if you look at a cross-section of wood, this is what you will observe. It's a micro-level structure that contains cells, also called tracheids or fibers in some context. They are hollow, and in the cell wall of that structure, you will find a very important biopolymer called cellulose. Cellulose is a linear homopolymer that contains glucose repeating units. And it's mixed in a composite type of a structure with a polyaromatic compound, another biomacromolecule called lignin, and that makes the cell wall. When we extract those fibers, they flatten up, and this is what makes paper. And paper is another beautiful example of amazing materials. Paper has been around civilization 2,000 years ago. And I would say that the first nanotechnologies involve actually paper fabrication, right? So all time ago, the chemistry of colloids and surfaces were heavily involved in paper making. And we lost track of that, but it's something that I want to bring back. But today, maybe, recognizing those fibers that you can flatten up in a two-dimensional network, those fibers 20 to 50 microns in width, depending on the botanical origin, at the same time contains very beautiful structures that you can see in the holes across the cell of the walls of those fibers that allows for communication. So the biology here also plays a very important role, and the transport. But those fibers are, at the same time, composed of smaller structures that we call nanofibers. That's what you see in the recent screen there on the far right. And if you hydrolyze part of those microfibers, then you find yet another structure that is very interesting because it's crystalline, and that's what we call cellulose nanocrystals, right? So in nature, we have this already, and this is a, very short introduction to nanocelluloses that some of you, not all, I suspect, know about. Now, interestingly, if we go and shift our attention to other materials in nature, including crabs, shrimps, fungal species, insects, you find yet another biopolymer that is very important that is called chitin. And chitin is sort of a cousin of cellulose. It's essentially the same backbone, the same glucose repeating unit, but rather than having only OH decorations, contain acetylamine groups in that structure, and that's chitin, very similar to cellulose, but has the potential by a process called deacetylation to open up those amino groups that can become, depending on the pH, cationic. So on top, we have an uncharged material. They can be negatively charged depending on oxidation and other processes. In the bottom, something that is a precursor to cationic charges. And as is the case of cellulose, they also form in nature sort of polygon structures that can be unraveled and then reduced to nanofibrillar chitin. And if you do hydrolysis of those fibrils, you can obtain chitin nanocrystals. So this is very fascinating to me because this is the nanotechnology of nature that has been working by evolution. And if we look at the sizes of those materials, at least the lateral size, I don't want to say diameter because these materials are not circular in cross-section. We are dealing here with 5 to 20 nanometers. This is an arbitrary number, but around those values. And if we look at the crystals, then it will be yet a little bit thinner, 3 to 5, 7 nanometers. And the length, now you can measure more easily, can be 100, 200 nanometers, right? So this is what we're going to discuss today. And I just start by saying that some of the most beautiful nanotechnologies using now wood, back to the principle wood, don't necessarily need to deconstruct wood into those nanomaterials. We can use wood as it is, and that's what I will show in the next slides, because we can unravel from the structure of wood those nanomaterials to play a function. In this case, with the idea of recycling wood from construction. And it sounds very simple, but actually the science is pretty deep in this area, and that's the beauty of this. Think about the need for recycling wood, as many other materials. Now we face this challenge of the fossil carbon and the need to replace fossil carbon with biological carbon in the materials that we make. It's not about decarbonization. Decarbonization applies to energy, but when it comes to materials, we depend on carbon. We cannot survive if there is no carbon. It's more about defossilization, meaning replacing fossil carbon sources by biological carbon and renewable carbon. And wood is a renewable carbon that we can access by the process of biosynthesis, as is shown in the slide on the top right. If we look at the timeline from 0 to 500 years, in the process of creating wood, nature uses CO2 from the atmosphere, uses water, and sunlight in the process of biosynthesis to produce plants, and that includes forests, trees, and those we use for construction, and those construction have a limited service life, right? It can be 100 years, 60 years, 200 years. You know many examples of constructions that still exist today for thousands of years. Anyway, circularity is very important. Once we reach the end of life of those materials, we have the problem of construction and demolition waste, major pressure in centers, right, cities. And this is the case that recycling of wood is very limited today. So what to do? And this is the best, I think, most beautiful example of using nanocellulose to repurpose wood, and I would say to upcycle wood, because you start with a material that is a waste and ends up being a stronger material than at the beginning. And this has been tried here in our earlier work with decayed wood, with waste wood or sawdust. And the key issue here is that we take those pieces of wood that are split, we run a process of delignification. Remember, I mentioned lignin. We remove the lignin, the polyaromatic glue that hold the fibrils together. And then we apply a solvent for cellulose. And then the cellulose will change the state. It will change from a solid state to a solution state. And in that process, what you will see is that the cellulose that is initially in the form of nanofibers will become now nanofibers when the solubilized cellulose is regenerated. This is a process that is commonly used in textiles. You take a cellulose dissolution, and then you use an anti-solvent to regenerate cellulose, and then you get the material, the wearable that you want to use, right? In a very simplistic way. This is the same, except that we don't remove the cellulose dissolution that is being dissolved at the interface. We keep it, and in the process of regeneration, the memory that exists in that material, the interface, goes back to the nanofibers that are native to the fibers, and that's what you see in green. And those nanofibers, when find each other in the anti-solvent system, then they glue together. So this is an issue of adhesion, having hydrogels connecting with each other in the form of nanofibers and making a structure that now glues together or heals the pieces of wood. Very simple. And the finding here that is very interesting is that the type of material that is obtained, if you look at the far right, in red, that heal or glue wood that we produce from the separated pieces of wood become stronger than the natural wood and very competitive against any other materials that you know, like including engineering materials, right? So this is an example of upcycling wood using nanotechnologies. Very simple. The second example along the same lines, maybe also about at the same time with our researchers, in this case in Finland, what here we did was to take the same material, wood, but now apply carbonization. So in this case, like in the previous one, we take the pieces of wood or a slab of wood, we delignify with a very simple process, remove the lignin. That lignin that is removed can be reused for other purposes, so nothing goes to waste. And what remains is a skeleton that is basically cellulose, and that skeleton that you see in the middle can be carbonized. And we found that carbonizing the material at high temperatures produce these structures that you see on the right. And if you have seen the previous slides, you can recognize that they take the forms of fibrils on the surface, right? So we are in a way, again, unraveling the nanofibers that are in situ so that they become structures that we can use. And our researcher, what the researcher proposed, okay, these really are no more than vertically aligned carbon micro and nanofibers that exist on the surface. They have to reveal also the structure of the wood, the nanofibers that we have talked about, and then you can get this type of a structure that is very interesting. And remember, because the cells of wood are hollow, that means that here we have sort of channels that can be used. And of course, the first things that come to mind is to use those channels to trap light. So if you shine light on the surface of that carbonized wood, the light will go in and will then be scattered multiple times, will be absorbed, and very little will be reflected. And what we found exactly is that total reflectance, depending on the wavelength, for a non-engineering wood carbon, a carbon that has been carbonized at low temperature, different than what I have shown, has a quite high total reflectance. But the material that I'm talking now with these microarrays is, or can be considered a super black material. Only 0.36% will be reflected back. That's cool because this type of material is very interesting for many technological uses. So this is the simplicity of nanotechnology in a different fashion, using nature. And this is important for many reasons, right? Anti-reflective materials are hot topics. The case of Vanta black is you know, quite nice to check. The fact that you have an object in 3 dimensions, and if you coat it with the Vanta black, the so-called Vanta black, then you don't see any shades. There is no light reflection. It's very low light reflectivity. And therefore, this is a great solution for many uses, like in telescopes, in optics, but also in defense and military applications, and many more, where you want to have anti-reflective surfaces. So this is the case of a material that is produced in clean rooms in a way, very sophisticated methods, and expensive. But here we have the material that I just introduced competing with Vanta. Not the same level of reflectivity, a little bit higher, but nevertheless, in a way produced by using cheap methods and using natural materials. One further discovery this year was that if you take pieces of wood and you apply the process that I have explained, then you will have an optical welding, meaning that those pieces of wood will also collectively work in such a way that you don't have reflection, and you have now achieved a larger surface area. And that was tried with different types of wood species. You see those on the top. So this works very well. I already explained some examples, but maybe you can think as a one that is quite interesting from the energy point of view is energy harvesting. This is an example from colleagues in Maryland, taking pieces of wood that are black to absorb water, sunlight, absorption of sunlight, and then heating locally the surface, and that promoting capillary forces, wood evaporation, desalination in this case. So they can be used for many things, like in this case desalination, or simply to convert sunlight into thermal energy, because this is a super black material, right? So I just want to stress again the beauty of using the nanotechnology that is already enmeshed in nature. Since wood is a material that is elastic, is strong and elastic, but not compressible, this is different. One aspect here that we also advanced recently was following the same sort of methodologies, the lignification, taking wood, removing lignin, and keeping the cellulose and the so-called hemicelluloses in the wood. We have a structure that you see in the center that can be oxidized and then reduced in a sequential manner with a very simple chemical method. So we did wood oxidation followed by reduction. In the oxidation, we obtained oxidized groups of the cellulose, especially aldehyde groups. And then in the process of reduction by very simple chemical treatment, then we obtain the transformation of the aldehyde groups to OH groups. And that's what you see in the far right. What we see is the cellulose chains becoming all decorated with OH groups, as is naturally, but you see also the breaking of the cyclic unit there is breaking. So what we're facing here is amorphization. That is, the mechanical strength of the material will be reduced because we're reducing the crystallinity, we're open those rings, and then the material will become compressible. So from wood directly, in a very simple process, we obtain something that looks like a foam, and in this case, it's a sort of a simple way, taking wood, removing, and doing the reduction, the oxidation and reduction to obtain that is a material that is compressible in one direction, but not in the other direction, because wood is an isotropic material. And of course, if you want to then modify and make this material water repellent, of course, there are many different methods that can be used. And today, those wood foams can be fully hydrophobized, can be immersed in water, and still resist water. So it's quite nice, simple technology that can be used for many different purposes. A recent development along the same lines, because I still stay with wood, that is my favorite material. What if we take the lignin in wood, we dissolve it, but we don't remove it, we keep it. What we found is that if we retain the lignin, we dissolve it, but don't remove it, that lignin will find each other, will be forming clusters, and it will be relocated. It will be moving away from the middle lamella, so-called middle lamella, and the inside of the fiber cell walls will go to the surfaces and will form spherical structures. So that's what we call retention of lignin, followed by clustering and redistribution in wood. And you can see some of those lignin spherical structures there that can also go to the surface of wood. And what we found is something that is also quite elegant in the sense that we are just dissolving lignin, letting the lignin to stay where it is, reconfigure on the surface, and produce a self-hydrophobization of the piece of wood. So we go from the top to the bottom, what you see there. In the next slide, I will show a video how this hydrophobization is quite interesting. But further, the fact that now we have a material that is hydrophobic, that can be used in construction. If we take these pieces of wood and you have some given slope, then water will roll off the piece of wood. And that can be interesting because what we have here is solid liquid contact as the roll of the droplets roll down. Then there will be contact, electrification, and then what we have here is an example of solid liquid trap generation. So back to the idea, the first things that comes to mind is to have raindrops, rainfall, water falling on the wood, letting it roll down and producing electrical energy by the typical process of trap generation. Very simple. So first, self-hydrophobized wood, very high contact angles. You can see we press a droplet there. It doesn't really stay. And then we created a little bit of artificial rain in the video in the center. Of course, that's a very low surface area, but nevertheless was tested. If we put electrodes in strategic places, we can collect the electrons that are generated, and now we have power generation. Right? Very simple example of power generation using raindrops in wood. Maybe, I think this is maybe the close to last to wood example. Is the case of the most recent work was in an exhibition in Osaka in the Canadian Pavilion. It's the idea of using wood to make a leather-like material. And what you see here is a soccer ball made of wood, but it's very light because we have placed some of the methods and approaches that I have presented earlier to make pieces that are very flexible and you can stitch and put together in a structure that looks like this, right? So this is in development, but it's quite exciting. Very simple nanotechnologies to produce leather. And as you know, leather is one of the major challenges from the point of view of materials because they have a very high carbon footprint, and there are many environmental issues associated with leather production. And this is, of course, a topic of research that is very hot these days. So enough of wood. What I have explained so far is playing with the hollow cell structures of wood that you see on the top left. But I have told you that we can produce also nanofibers and nanocrystals, and this is what we do. We take wood, the fibers in wood, unravel those nanostructures that I have already introduced. I show here the same to emphasize that that requires some mechanical energy. We can apply enzymes, chemical energy, mechanical energy, or a combination, and that helps us to deconstruct wood into nanofibrils and nanocrystals. And what to do with those? Of course, the fact is that those fibrillated polysaccharides or celluloses can be used in a process similar that I introduced earlier for the case of wood, where I indicated to you that we have fibrils at the interface gluing together. And I didn't mention this, but those fibrils are forming a hydrogel. So now I want to bring that new word to you. We are working with nanomaterials, nanofibrils, and also with hydrogels. And what you find with these structures is that they love water, they get hydrated, they bind water, tremendous amounts of water, and they produce hydrogels. And those hydrogels can be then used, whether in the form of fibrils or nanocrystals, in a process of water removal by drying, by different methods. And when we do that, then that process that we can call a reassemble process that is bottom up can lead to materials that are of very high interest. And I have no time to show all the examples going from medical devices and others, but some very simple examples that I want to share with you. So let me talk about nanofibers, and at the end I talk about nanocrystals, right? That would be what we have ahead. Starting with cellulose from wood, and then finalizing with chitin nanofibrils and nanocrystals. So cellulose nanofibrils. First thing, since the fibers and fibrils like water, it makes sense that with these guys we can produce or stabilize foams. And this is an example of what we observe when we take a surfactant, water, injected air, and with the surfactant, in this case, and sodium dodecyl sulfate, SDS, we get a volume of a foam that increases, but then after we stop air injection, the foam starts to collapse by a process that involves water drainage and also ripening. But if we take the same foam and we add fibrils that I told you are highly hydrated, that forms a hydrogel, then the observation is that those foams within the presence of the CNF, cellulose nanofibrils, are quite stable. You see the foam volume stays with time after you stop the introduction of air. So in the first case, we have foams that are wet foams become depleted in water, becomes more like a dry foam and collapse. In the case of foams that are produced in the presence of cellulose nanofibrils, we have high degree of hydration. We have in situ a hydrogel, and that hydrogel, if we look into the structure, will really prevent, by rheological effects, the drainage of water. And then the foam will be stabilized. Very simple way to take advantage of the hydrophilicity of the nanofibrillar cellulose. Expanding a notch up, going from hydrogels to binding. Same case, we take the material. In this case, we created a foam not using a surfactant, but using silica nanoparticles, another way to do it. We added water and ethanol and a gas in a pressurized systems to produce a foam in a dispenser, right? So that foam will have a very short lifetime, and at the beginning you will have a nice foam, volumetric foam, but it will collapse, as you can see in the picture on the right. But if this time now we add nanocellulose, there are these guys here, what you're going to see is something different outcome, where a very small addition of cellulose nanofibrils, by the effect of gelation and binding to the particles, what you're going to observe is something that is very different. It's like a foam mimicking more or less the texture of a shaving cream that contains the silica nanoparticles that are part of the reason why we get a foam, but now stabilized with the fibrillated cellulose or the cellulose nanofibrils. And those foams are super stable. So with a very small amount of this fibrillated material, we get something that is quite different, right? So very important. And that speaks to the fact that you have a hydrogel at the interface between the bubbles. And at the same time here, when you remove the water, you will densify, solidify the foam into a solid foam. And what we have found is that that solidification of the solid foam with the particles is due to a network that is produced between the fibrillated cellulose and the particles. This is shown here, cellulose nanofibers, particles, in the previous case, silica nanoparticles, and I have here several examples, very small particles, a little bit bigger, and the biggest to the right. Regardless of the particle size, the binding capability of this hydrogel of cellulose is very big, and when you remove the water, capillary forces will tend for the fibrils to be surrounded and tied very closely to the particles and form a network. And that network, if you remove the particles by this solution, will be looking like this. Beautiful. The funny thing is that we tested that binding ability of nanocellulose or fibrillated cellulose with different particles as shown on the top, silica, iron, lignin, clay, titanium dioxide, pollen, polystyrene. It can be cationic, anionic, hydrophobic, hydrophilic, amphoteric. It doesn't matter. The removal of water will coalesce the structure around the particles and will stabilize those structures, right? So it's a very powerful particle binding. I think this ties a little bit to the initial thoughts when we were using wood. It's an amazing binding ability. Finally, for cellulose, nanocrystals, right? I want to talk briefly about nanocrystals because I don't think all of you are familiar with nanocrystals. Who are familiar with cellulose nanocrystals? Just to, okay, oh, good. Roughly half, good to know. Let me introduce this nanomaterial that is absolutely amazing, and I hope that you can also think with me about possible applications. This is the most amazing nanoparticle that you can find, not only beyond nature, but also those that can be synthesized in the lab. Here, this particle is a rod-like particle that I had already introduced, but it has chirality. Those crystals are right-handed twisted. First thing. Second thing, and there are some references there that you can consult. The surface energy is different depending on the plane of the crystal. So there are some that are more hydrophilic, others are less hydrophilic. And that will mean that they will have the tendency to absorb at the oil-water interface or around liquids, at the interface in liquids with different surface energy as well. And the last one that I'm not going to explain is there is a material that is chemically anisotropic. They have different ends in the crystal. And that means, as we have illustrated in this publication some time ago, is that those nanocrystals can be fixed on a surface and on in one direction, right? So that can lead to many applications, like in photonic materials and others. But I'm not going to discuss that. I just show the references and some evidence in TM how gold nanoparticles are grown or attached only in one end of the crystals, not in the other end. So they are anisotropic. Beautiful. Beyond that, they can be, or they can have piezoelectric properties and tribogeneration properties. So a simple, mundane material that now, when we use it as a nanomaterial, as a nanocrystal, can have those effects that I have just mentioned. Further, they form mesophases in water. We disperse this in water, and they will form these chiral nematic structures. You can see that on the right. And if we remove that water, then the structure will collapse and will lead to the so-called structural color. This is very well known, very well reported in the community. And the pitch, that is that distance for a full helicoidal distance, can be changed depending on the composition of the suspension, right? So great opportunities to make here iridescent films, coatings, as well as coatings with different color reflection, selective light reflection. So this is what we have. If we have water, nanocrystals, and we remove the water, that helicoidal structure, chiral nematic structure will be preserved, and this is in a way what is reflected in this cross-section of a film made from the cellulose nanocrystals. You get the point. Now, the next step. How to make this viable not only in a coating or in a film, but in a hydrogel. And I will skip all the details. You can find those in the reference. But an observation here is that if we have the nanocrystals in water, and we replace water in a hydrogel with an organic solvent, now we will get an organogel. And what we found is if we do this in a clever way, that chiral nematic mesophases that I have explained will be preserved even in the liquid after removal of water and replacement with an organic solvent. And you can see that by this reflection, bluish reflection that you see in the organogel. So of course, what we thought, okay, if this is working in organogel, now in the organogel, that organic fluid can be evaporated, can be removed, and now we can get a foam as opposed to a film or a coating that preserves that chiral nematic structure. And that's what we have here. So we went from left to right to produce aerogels, cryogels. That's what we call these solid porous elements. And the beauty of these structures is the following. If the crystals that are rod-like form a foam that is random, the specific toughness versus a specific strength will be rather poor. There is no assembly in a given direction. If you have a nematic phase, if the crystals are oriented, you will gain an anisotropic behavior and the mechanical strength in one direction will be improved. But if we have a chiral nematic structure like the one that I have introduced, then you will have a very strong material. So that was what triggered our imagination to go to this type of material, removing the solvent to leave behind the crystals with that structure. And that's what we did, and obtained the little foams. We can call this an aerogel, very high surface area, very small pores, very, very light, low density, but enough to sustain the load or the weight of a brick, as you can see in the little experiment here. We're talking here 170 tons per square meter. Super strong material with very little mass, a material of very low density. So we went from hydrogel to organogel to a structure that is lightweight and has a very good loading ability. And what is best? We have preserved the chiral nematic structure. That pitch will be there, and if the pitch is compressed by mechanical loading, the pitch will be reduced, and the foam, or the aerogel, in this case, will change color. So here we have an optomechanical responsive material made from cellulose nanocrystals. That was already a long time ago, 2020, 2019. But you see the beauty of a very simple material that has been assembled in space in such a way that we get similar mechanical response to some of the strongest materials using a very simple and cheap nature-based material. Okay, enough of cellulose. Let me shift a little bit to chitin, because chitin has become a favorite player in our lab. The beauty of chitin is that we have similar structures, but you have acetylamine groups. And if you remove the acetyl groups, then you will preserve amino groups. And the balance between the amino and acetyl groups can bring really quite nice knob to regulate the surface energy of the material and the surface charge, that in this case is negative, low pH. So it's amazing. With cellulose, this is a little more difficult. So let me talk about that. How we make the cellulose and the chitin nanofibers. The process is very simple. You go from left to right. We went to the fish market. We bought a lot of crabs, 150 kilos of crab. And then they were processed. Nowadays, we learn that we can do better chemistries, mechanochemistries, sonochemistries to accelerate the process and to be a little bit more sustainable. But at the end, what you have is those white flakes. These are the chitin nanofibrils. And if you put water, you get a chitin nanofibril hydrogel. That's what you see in the very far end. And those materials, again, shown here, can have these properties that you have acetyl groups, as shown here in the orange diagram. Or if you remove those, you have amino groups. And if you have the right pH, they can be activated. So the process is a process of removal of the mineral part of the crab shells or the shrimp shells, then hydrolysis, and then sonication, and what we get is either fibrils or crystals. In this case, I'm showing nanofibrillar nanochitin. And these nanofibrillar materials are very interesting because in nature, there are biological architectures that are based on mineral, protein, and chitin that make excellent structure for fracture dissipation. So mechanically, this can be very, very strong. And an example that you can Google is the mantis shrimp that with a sort of a hammer and with the help with very fast movements, it can shatter the seashells that are very strong. So very strong chitin-based materials. So that inspired a little bit what I now show next. That involves also hydrogelation. So remember here, the common topic is hydrogels and interfaces, right? So the next example is quite nice for that process. What we took was the chitin nanofibrils, we added calcium and phosphate, and then we exposed this to ammonia gas. That ammonia gas is going to diffuse into the hydrogel of nanochitin by a process of ion diffusion gradient gelation, hydrogelation. And what you are going to see is that because of the diffusion of the gas, then you will have a structure that, to our surprise, will evolve into a periodic structure. That was unexpected. I mean, you can get a hydrogel that is more or less uniform, but the beauty of this is that here we prove a sort of an oscillatory type of process where we gain hydrogelation in two stages, consecutive in a periodic fashion, one where we have mineralization of the mineral precursors, and the other one where the organic phase, the chitin, also forms a strong hydrogel. So what you see here in areas of light and darker regions is nanochitin hydrogel with a mineral-rich phase. And that's what you see here in actual movement, where you see those phases, right? So we have continued doing this work. That was already some time ago. Now we're working with nanochitin mixed with nanocellulose, and we see the same process. It's like a periodic process of hydrogelation where you have interlayers that are organic and mineral. And that's beautiful because if you recall the natural structures that I mentioned earlier, they have those type of layering between mineral and organic phases. Of course, this can be anisotropic, and you can make in different fashions depending on the mold that you use to get this hydrogel. You can notice these structures in the example there. And if you take those hydrogels and you shine light just to demonstrate that they are anisotropic as expected, they will reflect light or transmit light depending on the orientation, right? So it's quite cool system. If we take that hydrogel with those multi-layers, and now we go to the next step, we remove water, the water that is present in the hydrogel. If we do hot pressing, the material will become a flat film, you see there. And that flat film, because the expectation of the initial hydrogel, will be formed structures that will be a little bit similar to this brick and mortar structure of natural abalone, layers of organic, inorganic, protein and mineral layers. And this is what we obtain. We obtain a material that is shown there in red, whose location in this plot of a specific stress versus a specific modules makes it quite competitive with some natural materials and man-made materials. You can compare this with cortical bone, abalone, natural nacres, right? That takes long time to produce, but this is produced in a short time. And the principle of work is exactly what I explained. It is automatic oscillatory formation of the hydrogels with a mineral-rich and organic-rich phase. And notice that the addition of calcium phosphate was done at a given ratio so that we produce hydroxyapatite because we were targeting bone-like materials in this case. So that was successful and quite nice example. Because I'm talking about interfaces, now I have introduced a solid, beautiful multi-layer. Let me add oil. I haven't talked about oil, and I want to introduce a case of oil-water interfaces. In our community, cellulose, chitin, nanocrystals, nanomaterials, especially the nanocrystals, will have the tendency to go to the air-water interface, to the oil-water interface especially, stabilize the interface, and in the case of emulsions, oil in water, oil in red, the water in black, they will go to that interface and stabilize the emulsion. That's called Pickering emulsions. So we have been using, for many years now, all of these materials to produce very stable emulsions, high internal phase emulsions, etc. I just want to highlight again why chitin is very special for making foams, as explained earlier, but now to make emulsions. At the oil-water interface, they will be absorbing because they are amphiphilic, as I explained. And then what we have here is a very simple experiment with a bimorph where we put a droplet of oil immersed in water, coated with nanochitin. Then on top, we have a capillary tube connected to an actuator. We have another oil droplet, also coated with absorbed nanochitin. And then what we are looking to do here is to use the nanochitin that is absorbed at the interface at different degrees of deacetylation. Different degrees of acetylation. Remember that I told you we can remove the acetyl groups and control the surface energy of the nanochitin and eventually the charge. You can also change pH and strength and gain further possibilities, right? But for the case that I have here, the simplest case, we have on the left and on the right 2 cases where the droplets will fuse with each other, will coalesce. The chitin that was absorbed was not enough to stabilize the interface. But the one that is in the middle, no matter how much and how hard you push, it's not going to fuse. Coalescence won't occur. And the difference between those 3 is the same nanochitin, but here we go from low degree of deacetylation, medium degree of deacetylation, high degree of deacetylation. So there is a sweet spot that allows us to produce a quite nice system that resists that coalescence that I have alluded before. This we have used for other purposes, dispersing carbon nanotubes, graphene oxide, and what we have found is that we can control the degree of acetylation, deacetylation to achieve the best possible results. So that's what we have. Now, I want to make or transfer these emulsions and dispersions of chitin into lightweight materials, similar than I did with the cellulose, right? So same idea. With chitin is particularly interesting because you can make it cationic. So here we have nanochitin. We add a cross-linker glutaldehyde. We have a hydrogel here, and we freeze the material. Then you will have ice nucleation and growth, nice ice crystals, and what that will do is push the liquid to the interface, will confine the chitin at the interface between the ice crystals and also the glutaldehyde. And what that means is that you will get very high degree of cross-linking at the interface between the ice crystals and the continuous phase. And what that means that you obtain a frozen gel that if you increase the temperature will become a hydrogel, but if you then freeze dry and remove all the water, then you will obtain a so-called a cryogel, similar to aerogel that is where the water is removed by freeze drying. These materials are great because of that process of ice nucleation and confined cross-linking at the interface between the ice crystals leads to hydrogels that are very strong. You hopefully observed that we took it from dry state, immerse it in water. They absorb a lot of water, and then there they are, and they gain the initial shape, but in a much larger sort of volume. And if you dry it, then you will get a cryogel that is mechanical, highly resilient, and strong. And this is due to ice templating. So that's a method that some of you are working, ice templating of chitin nanofibrils with a cross-linker. Now, one evolution, an extra evolution that is actually quite exciting now. And now I mix the ice templating with emulsion templating using nanochitin. So bear with me. It's a beautiful example. This is recent work. The idea here is to produce bicontinuous systems in the form of emulsions and cryogels. Systems that you don't know what is in, what is out. What is the continuous phase, what is the dispersed phase. That's what we can roughly call a bicontinuous system. This is very, very well known in the literature. So an example, you can take an oil called lutein and mix it with water, low concentration on the left, high concentration of the oil to the right. And this lutein will have a phase behavior in such a way that at low temperature will form a single phase. But if you warm up the system, increase the temperature, it will go to a transition and there will be phase separation, right? So upon heating, we will see phase separation between the oil and the aqueous phase. A low concentration of the lutein, we're here, high concentration, 50%, we're here, and here in the middle, we observe this minimum. And this minimum is a special sweet spot for phase transition where you tend to find the systems of minimum energy, and then you will tend to have bicontinuous systems. So, in other words, here we will have lutein dispersed in water. Here we will have water dispersed in lutein when you increase the temperature. But here in the middle, we will have something that is neither of the two cases. It's a system that doesn't know where to go, oil in water, water in oil. That's a bicontinuous system. And what you see now is the two cases. Let's take the case of the 50% lutein in water, and we increase the temperature. This is what is going to happen. There will be nucleation and growth in the phase separation. The lutein will be nucleating as droplets, bigger droplets, and that's what you will see here. What happened when we're here? I want you to pay attention to the red frame here and the video on the right. You will see a phase separation, and at some point it will be bicontinuous, but that bicontinuity is not going to be persistent. It will disappear with time very quickly. Why? Because this system is very unstable. So what to do? What is the answer? Chitin. We add chitin. Chitin will add the stability and will jam and freeze that transition in such a way that we keep the bicontinuous structure. That's what we did here. In other words, chitin was added. In the left case, we have lutein in water. In the right case, we have water in lutein. In the middle case, we have a bicontinuous systems where the red nanoparticles there are nanochitin, and they will jam. They will stay in the aqueous phase and will jam the structure. So the bicontinuous system will be preserved. That's an example of bicontinuous intraphase jam emulsion gels. How does that work? Very quickly, I go now. Left, one case, right, another case. In the middle, something that is very viscous, doesn't flow when we invert the vial. When we freeze the material and do imaging, then we observe something that reminds us of bicontinuity. So we have a system that is bicontinuous. And then, if you remove both the oil and the aqueous phase, so we take this, we heat in the presence of nanochitin, we will have a bicontinuous system, and now we remove the oil and the water, then we're going to template the bicontinuous system in a solid structure that is made from nanochitin alone. And that's what we observe here. A cryogel that is very lightweight, as we expected, but the beauty is the internal structure. The internal structure of the cryogel is such that when we observe it's very rich. It reflects the initial bicontinuous system that is shown here. And at the same time, if you look in detail, it will show some smaller structures that also reflect the original material. And of course, as you can expect, these materials have very high internal surface area. Now, why I'm insisting in nanochitin for this purpose? This has been done with silica. Silica spherical particles are great to structure. But to achieve similar system, you need a lot of silica particle loading. In the case of the rod-like nanochitin, the loading that is necessary is very little. I will show in the next slide the numbers. So for structuring this material, With silica, we needed 5% of silica. With this guy, we only needed 0.6% of the chitin nanoparticles, right? Now, why do we do all of this? Of course, there are many applications. I'm not going to refer to anyone, but advanced material templating, microreactors, CO2 capture, energy materials, control release systems, many applications that I skip for time. Okay, I'm finishing now. I just talked about cellulose and nanochitin. I didn't talk about lignin at all, but that's, of course, a subject of work in our lab. And I didn't talk about something that is extremely fascinating, that is producing micro and nanoparticles from other sources. Lignin, this is already well reported, producing lignin nanoparticles, right? But also from tannin and tannin derivatives, there is a diversity of morphologies that can be produced from tannic and tannic acids that are present in the bark of wood. And then the case of triterpenes, betulin, some beautiful morphologies there, hedgehog type of structures, flower-like, needle-like, those can be controlled. We have been looking in depth into this, especially for betulin. There are amazing results as far as the chirality of the crystals. And this is to be reported. But I wanted to say, okay, it's not only cellulose or lignin or chitin, it's also what we find in bark that is a waste. Conclusion, I just invite you to take a look at this Stockholm Declaration of Chemistry for the Future that was signed this year in May. You can read the text here. I invite you to read it. That was with the parents of green chemistry there in the bottom, and Ben Feringa, a Nobel Prize winner in Stockholm. We assembled and we drafted this declaration, and I like some of the paragraphs that are written there. You can read this. But this is the commitment that we need to make, that in the future we will work and implement chemical products and processes that proceed in a manner that integrates the goal of reducing or eliminating harm to people and the planet by design. So I invite you all to work on nanotechnology, advancing that function. A little bit about the Bioproducts Institute. It's a great ecosystem, a little bit smaller than what you have here in the Nanotechnology Institute, but nevertheless, we have a group of people here working in different areas related to bioproducts, using chemistry, biology, material science. So it's very nice, and we are very open to collaborations with all of you. And my acknowledgement to the people who did the work, in fact, our researchers in UBC. Some of the work that I presented was also carried out in my affiliation 5 years ago in Aalto University of Finland. So my thanks to all of them. They are the reason why we work and we have achieved some level of success. So thanks to them. With that, I finished. Thank you so much.